Thanks very much indeed, Lou, for stopping right there, right in the middle of everything. That's a brilliant place to stop because there's so many places to go to from there. Thank you very much for a very thought-provoking talk as well. Very nicely done once again. Can I throw the floor open for any questions?
Yes, can I have the slides, Lou?
Oh, sure. I make the slides available. Let me see. Should I send it to John and then it'll become available to everyone?
Yeah. Send it to me. That's fine.
Right.
Send it to me. I'll make sure they get public.
In the last part, I wanted to say more about what happens with Garnett's elaboration of the Feynman checkerboard, but I haven't thought it through enough. So that's another point of departure for doing some more.
Yeah, you flip through very quickly in the end there. So that's because you want to think more about it, or the checkerboard thing. Do you want to return to it?
I'm sorry?
You want to return to the checkerboard and explain it more because you went very quickly there.
All I was saying was that in the checkerboard, you can set it so that it's real. The differential equation is real. So that the solutions that you're picking up from the checkerboard are real solutions. And that's an example of a Majorana situation already, just in the checkerboard. But I came down into a solution to and thinking about the Majorana equation in 3+1, right? So what Peter and I did in 3+1 can be specialized to 1+1, and then we can think about how it relates to the checkerboard. And then remember, Garnett has a more elaborate way of thinking about the checkerboard, which relates to a lot of philosophical issues in physics as well as new physics. So altogether, that needs more thought.
So for me, this relates very much to neutrinos, superconductivity, and the fermion boson. When you either look at fermion pairs or boson particles, and the commuting and anti-commuting properties is like either you look at the pairs or either you look at the splits of the pairs.
Well, as I was saying, the pairs that one is looking at here are, if you look at the algebra for one electron, for one standard fermion, the algebra makes it look like it's a pair. The algebra makes it look like it is a pair consisting of two Majorana fermions. So if you have a row of them, then the two electrons can undergo Cooper pairing, and they are then linked to one another. But one Majorana fermion from each is sort of left free on either side. If you have a row, then you can imagine that the row of pairs of Majorana fermions are kind of internally all linked with one another, and the two guys at the ends are a little bit free, and they have some correlation between them.
So, and then you can choose to look at them as fermions, or you can look at them as pairs.
If you look at them locally, they look like a Majorana fermion at the end of this stuff. I think this is Leo. This is Leo Kauffman and co. looking at these things, isn't it?
Right. So people have done these experiments where they measure the correlations in the nanowires. But the experiments are delicate, and there seems to be some controversy as to whether they have seen what they claim to see. If you look in the most recent issue of Physics Today, there's an article by one of the researchers talking about this and about the controversy.
perhaps we
What
should.
is the controversy? Is it detailed or is it complicated? Is it simple to explain or is it complicated to explain?
Is what complicated?
The controversy, it's complicated to explain or not complicated?
Well,
Can you explain that?
well, I mean, people have done this experiment, and maybe more than one group, and I think they just are not fully convinced that they did what they had originally claimed to do.
I think that's a pretty involved discussion if we want to go into that area. Perhaps we could get one of those people in to talk to us at some stage, and then we could further this thing from the experimental point of view.
Remember, if you said that you have particles, if you say that an electron is composed of two particles, well, you're not going to see them, right? At best, you would see something about the way the mathematics of that decomposition suggests something in observation, but it's probably much subtler than seeing a quark. To imagine seeing a Majorana fermion out of an electron, which it's interesting because at the mathematical level, it's just a plus bi squared is a squared minus
Don't forget, Lou, that when you get into this quasi-particle domain, what one's doing is one's splitting the electron. One could be associating the electron with more than one.
Yeah, that's an important point. Another situation in which these ideas are matching in principle is not just to individual electrons, but to quasi-particles, which are collectivities of electrons. So if you have a current running in a very cold plate and a magnetic field perpendicular to the plate, then the electrons form vortices around the lines of the magnetic field, and those vortices are conjectured also to have this kind of Majorana fermion behavior.
I think there are plenty of experiments that can be carried out in that domain and will be carried out further, and a very interesting domain it is too. So if we can contribute to that in any way here as well, I think that's going to be good for those guys too. Ines, I saw you were on for a question at some stage as well. Is there something you wanted to ask?
Yeah, it was early on, Lou, when you were introducing with your diagrams for the braiding of the two Majorana particles, and you were you had that kind of equivalence of those two states where both had a kind of half twist, but you kind of topologically sort of pushed all of that over onto one of the particles.
That's right.
So obviously there's two ways to do that. You could assign that negative property to either one of those. Does that have any kind of knock-on effect when you start building up some of these larger systems? Like, is it a sort of convention you have to follow, or does the fact that you can kind of assign that negativeness to either particle do anything for you?
Well, if you assign uniformly the operators the way I did to the thing, then it will uniformly always take the ith particle to the I plus first particle and the I plus first particle back to the ith particle with a negative sign. It's a property of the algebra of those operators.
Yes. No, but what I was thinking is, but that's a choice you're making, no?
It's certainly a choice. I could, in fact, you remember how I wrote the operators, and they all had, I had a row of things, A, B, C, D, and then I wrote B, A, and then so on, each one in the opposite order all the way up the line. If I wrote them all in the exact opposite order, it would still work, but then the interchange would go the other way.
Yes, but I'm saying that that's still also a choice to have them all uniformly.
Yeah, it's a choice.
One way around or the other way around.
Yeah, it's a choice.
Is it possible to see what happens if those are not uniform in that distribution? I'm just thinking in terms of Yeah, to me, one of those diagrams you had that kind of each element has this kind of half twist, which we can't really say this is positive and negative. But if you push all of the twist over to one side, you can say, okay, well, the twisted one is negative, the untwisted is positive, and that allows you to get into the algebra.
Yeah. So of course, the assumption behind that is that however you manage to turn this algebra into an observer for the situation, and observables for the situation, that you would have done it in this uniform way, then you will get this kind of patterning. If you suggest an interesting exercise, suppose that I create the row of operators, but maybe I decide to write them in different orders, right? So one of them I do with a BA, and the other one I do with an AB, and the next one, and so on. Then I won't get a representation of the braid group as a whole, but the individual braidings will work in different directions.
Yeah, that's what I was wondering.
So then it'll give me a kind of more chaotic set of observations.
Yeah.
So one is making up, in this kind of theorizing, one is making up an observational framework that is as ideal as possible, and imagining that one can do that somehow.
Yeah.
And you should underline the somehow, because I don't know how you would actually observe the braiding of these particles. Think of that, right? Think of the original situation with the nanowire, and people are trying to get the correlation between the ends. But suppose that instead of that, they wanted to take one of those particles and braid it with the other particle. Well, then they would have to somehow have access to the particles, directly or indirectly, to move them around. And those particles are bound inside electrons. They aren't going to move in any easy way. So this nanowire picture is not going to submit to observations of braiding very gently, very quietly. It won't submit quietly to that. Maybe something else will, like the vortices of electrons. But people haven't managed to see that braiding either.
I think there is a way to do this. I think if
there is a way. You can break the pair, and then you can propagate that break through the chain.
I'll say that again.
Break the pair that you created with when you have the boson, and you can propagate that break across the link. So then you just take the half electron, one electron moves to the other pair, while the other one moves to the next pair.
That's brilliant, Joachim. You're absolutely right. You can propagate a defect, and that's really interesting. You're quite right. And in a nanowire system like that, Lou, you've got all sorts of things you could do, because you've got a quantum state which is extended, and you can poke at bits of the quantum state. You can try and break it in the center. You can knock it in the center. You can hit it with. You can do all sorts of things, because once you get the particles bigger than your technology is small, so we start looking at quasi-particle systems that are coherent over tens of nanometers, and we can now make things down at single nanometers. You can get inside quantum states. You'd be astonished at what can be done here in these experiments. And Joachim's point is extremely valid as well. You can get you can propagate a defect, and that.
Yeah, I think you can actually illustrate this as either you have a chain of pairs on one braid, or you have two braids of fermions. And they are identical. It depends on if you sum them or if you take them as individuals.
Mm-hmm. But all these suggestions, John, you're saying you want the particles to be fairly large, like quasi-particles.
And in the solid state, you can make particles quite large.
Mm-hmm.
The size of an electron in these systems that Leo's looking at are tens of nanometers. And so, and we're getting to the technological stage where we can go sub 10 nanometers. So you can poke around in the innards, because what you've done is in the quasi-particle electron, you've increased the size of it, and of course the phase coherence length in a superconductor is huge. So you're looking at phase coherent systems where you've stretched them out, and you can then poke, and those things are also bound. They're also stationary, so they're slow. So you can do something to them relatively fast.
Yeah, I actually did measurements at down to 20 millikelvin when I did research, and the electrons were stable for half an hour, didn't move anything. It was really, really quite.
I think as Quicycle, we should get together, Joachim, yourself, myself, Lou, you, a few of us should get together and propose some experiments. I think we should have a little panel discussion.
Well, that would be great to have a discussion about possible experiments.
Let's do it.
I'm sure that Leo would love to do some experiments. He's in a controversial area. I can see that from nature discussions.
Well, there was a time. Well, okay, let's get them involved. Those guys, I know these guys. Anyway, oh, sorry. Mark was asking me if he could ask a question. Can I pull Mark in for a second and then come back on that?
Sure.
Thanks, Sydney.
Yeah, I've got a question for well, Lou and Peter, really. So on Thursday, Peter gave a presentation of his sort of fundamental ontology, and it's really a question about where you both start from. So Peter begins with the most simple observable, or most simple phenomena in physics, which he considers to be space-time, mass, and charge. And Lou, you're effectively beginning with distinction and self-reference to some extent. And I suppose my question is
that's right. And I'm asking the question, what's the relationship between those two? Because when one begins in a logical or semiotic frame and thinks about building worlds by making distinctions, one isn't coming from physics, one is coming from a kind of cognitive philosophy, right?
Yes.
And it doesn't prejudice any physics, but then this prejudices very little physics either, right? If you start the way Peter starts, well, he's a physicist, so he talks about mass and time and space and charge, but where he starts in his most elementary place is what kind of language could you write? What kind of algebra could you write? What kind of algebras are even possible? And then if you look at what he does, he's actually analyzing what kind of algebras are possible given that we're going to have interactions represented by distinctions in this way, and then it starts to come out, right? You start telling a story of what comes out. Then he knows beforehand better than I what should be thought of as energy and what should be thought of as mass and what should be thought of as charge. He can spot it almost immediately because of his experience, right? If you imagined yourself as knowing no physics at all, then you won't spot where the physics is coming in until it hits you in the face. But I think both approaches are very similar. And of course, it makes sense to know as much as you can when you're supposed to be starting from nothing.
Yeah. Can I ask a question?
Peter, would you like to comment on that?
But Peter should have a comment about this.
Yeah. Comment and then, sorry, a comment first, and then I'll pass over to Sydney who wants to ask something. Essentially, I have another starting point, which is the rewrite structure.
That's what I was referring to.
Yeah, okay. Which I don't think people realize that, which generates these parameters and other things. And in the book I did, Zero to Infinity, I say where that comes into connection with the Markan distinction.
Yeah.
When you get to the nilpotent structures, that's when it comes into connection with those. So, but I start from this rewrite structure before I even do any physics or even mathematics, and then that would be another talk. There's so many possible ones, but Sydney wants to ask a question.
Sydney,
I just want to ask you, Lou, on the wider perspective about I saw in your slide you had 0 equals plus 0, 0 equals minus 0. My question is, can the nilpotent itself be identified as the distinction? And in that sense, can like the nilpotent as Peter writes it, can that be the actual distinction? And that
well,
I saw that.
Okay, so remember, remember at the end I was saying that, right? But the point is that when you speak of a distinction, you could be speaking of a very particular distinction, or you could be speaking of the concept of distinction, or you could be speaking of the notion that the whole universe somehow divides into what's observed and what is observing, right? The fermion, when it comes into being, is dividing the universe into the fermion and what it is not, right? If you're thinking in terms of universe as a whole, then universe acts on itself to erase the distinction that happened or to produce it.
Mm-hmm.
And at that level, the universe acts on itself to produce nothing, right? No distinction. And at that level, that's a nilpotent. It's okay. It's a correct kind of deduction at a very abstract level that universe itself is a nilpotent.
Okay.
You immediately ask what you meant by that, but then in laws of form, one has taken a symbol to represent a distinction, which could be that, and then that distinction acts on itself to produce nothing. And now you're in a bit of formalism where you've made the simplest nilpotent operator you possibly could, namely a little symbol which, when it acts on itself, vanishes, right? So that's the granddaddy at the level of signs of nilpotence. But of course, if you want some physics to happen in it, then you're better off elaborating it a bit so that it involves energy, mass, and charge. And that, of course, is what happens when Peter writes down his nilpotence. But those nilpotence of Peter's are very, very primordial. They're almost like that mark. Except they just contain enough physics to begin doing physics.
Right, right.
So I have a question.
Did that answer your question?
So you're answering in the affirmative, yes. Depending on whether you want to bring in energy, mass, or whether you want to bring a physical distinction, or whether you want to think of it as a semiotic sign.
Yeah.
There's multiple ways to look at it, but in the overall affirmative, your answer is yes.
Now, my experience in playing with the mathematics is always that I get a little surprised every once in a while that something more elementary than I thought produces a pattern that I like. That was happening in one of my slides this time. I didn't notice that until more recently, that if I just started with the 0-1 oscillation, never mind even having -1, +1, just the 0-1 oscillation, then the 0-1 oscillation thought about temporally produces the fermion algebra.
And that could also be thought of as in terms of the negation sign, the not logical function. Could be the, I was thinking of that when I saw your slide.
That's right. You have not 0 as 1 and not 1 as 0. You don't have negative numbers yet.
No.
You just have 0 and 1. But nevertheless, you have the temporal entity going from 1 to 0, and you have the temporal entity going from 0 to 1, and they together are nilpotents, and they form fermion algebra.
Okay. Thank you, Lou.
I thought it was the other way, that Peter's algebra had the fermion algebra and your algebra here had the boson algebra.
What was the question again?
I thought that Peter's talk was about deriving the fermion algebra, and your talk here was about the boson algebra.
No, my talk was always about fermion algebra here.
I need to look at it again.
Well, this must be a matter of terminology. Let me state what I call fermion algebra. Two operators, let's call them U and U dagger, and U squared is 0 and U dagger squared is 0, and U dagger plus U dagger U is equal to 1. I call that fermion algebra. It's a mutator, not a commutator. In boson algebra, you have a commutator of the two creation and annihilation operators. Now, do we have common terminology here? You saw me using Clifford algebra but that Clifford algebra is underneath and related to the fermion algebra.
I'm not so used to that terminology, so I will need to look at Peter's talk again and reinterpret it.
Okay. Any further questions? Anyone else like to jump in and ask Lou anything at the moment? Well, I've got one or two as well. So one of them, Lou. You're looking at an algebra here, and then a subalgebra, the Dirac algebra, then going down to the going down to submatrix algebra, that of the quaternions and of the Pauli matrices, and then going down even below that with these lovely epsilons and etas that you've been introducing. So it's layers inside layers inside layers, very beautiful. But then this unit imaginary keeps popping up as well. That worries me a little bit.
Wait, what worried you?
The unit imaginary popping up in the exponentials worries me a little bit. That needs to be in there. Because I don't think it does. You've got it. You take a combination. You've got the unit imaginary from your epsilons and your etas. Why don't you use that in the
well, that's a good question. Let me go back to the mathematician's question about that. Mm-hmm. Out of very little consideration, you find yourself looking at the split quaternions, right? You find yourself looking at epsilon and eta. From my point of view, I look at epsilon as the alternation of -1 and +1.
Yeah.
And eta is the time shifter. Mm-hmm. And epsilon and eta talk to one another and produce an algebra without any square root of -1 yet. But the square root of -1 appears as the product of epsilon and eta, the time-sensitive point of view, right? So I take that as the appearance of the square root of -1. And those generate the split quaternions. They haven't quite gotten to the quaternions yet. And then how do you get to the quaternions? And one way to get to the quaternions is to reach into your hat and pull out the rabbit of a square root of -1 that commutes with everybody, and drop the rabbit onto 2 out of the 3 entities that you already had, and lo, there's the quaternions, right? That's what people usually do, including myself.
That's right. That's what we usually do.
Another way of handling that is to say that you're going to take you're going to understand it in terms of matrices, so that the square root of -1 that you produced is a -1 anti-diagonal matrix. And then that's quite antiseptic. There it is, and you can put it into blocks and make things out of that, right? But it's still, you needed to do something else in order to get a commuting square root of -1. The square root of -1 that you produced when you formed the split quaternion algebra, the epsilon eta, was anti-commuting with some guys. So you can say, okay, I don't care. I'm just going to isolate you, and I'm going to make an individual algebra out of you that's designed to commute with anybody I care to. I'm going to give you a new name and clothe you as the square root of -1 that commutes. But I don't know how to do it otherwise. I would like it to come. I would like the square root of -1 that commutes to also come out of this sort of epistemological approach. But I haven't seen it happen without that clothing the paradox in the right symbolism method, which is a little strange, right?
Yeah, it is. It is, and you would think it would come out. I mean, there's another way to get the quaternions out of the proverbial 3-dimensional hat. So we could take it out of the hat here, which is to bring in, which is to bring them in by increasing the dimensionality from the toy model of a 2-dimensional thing to a 4-dimensional thing, a 3 + 1 dimensional thing. That pulls your quaternions in, but it doesn't solve your problem of having something that commutes with everything appearing in that as well. And But the question is, does nature need that thing that commutes with everything? Or is that precisely the point that that makes the distinction that one needs between things that do and do not exist in terms of the kind of solutions?
Well, I do think we still go round and round on this. Like if you were just thinking about Schrodinger equation, and you say, oh well, all right, the I isn't really I. It's really some kind of alternation between +1 and -1. So why don't I use it that way and think of it clockwise, like Garnett does, or the way I do in some things, and then I can take the Schrodinger equation and I can rewrite it as a recursion where there's no I. It's just flipping back and forth between plus and minus in a certain way, and then you want to be able to take the limit, and then you run into the problem when you take the limit, because in the limit the plus and minus oscillation goes to infinity.
Mm-hmm.
And so you need to turn it into a symbolic entity instead of a limit in order to use it. And you need to split the odd and even parts into two parts in order to have the limit make sense. And then you find yourself with the split that you work with of A plus IB.
Okay.
So one way of thinking about it is that split is because the oscillation has to go to infinity at the limit.
But if, as a physicist, I start thinking about what this oscillation is, what we're talking about in terms of an oscillation, I find myself thinking about something like something that's going round and round in circles, that's going from plus to minus, back to plus.
Mm-hmm.
That's not the only sort of minus you have. So there are lots of different square roots of -1 that one should be thinking about, not just.
Yeah, exactly. And if you go up to the quaternions, then you have an entire sphere of them.
That's right. You've got an entire sphere of them. But very beautiful. But even in the quaternions, there are different kind of negatives. One should really distinguish between the negative of I squared equals J squared equals K squared equals one kind of -1, and IJK is actually a different kind of -1. Because if you look at,
yes, right.
So and then one's looking at different kinds of square roots, and that makes things really fun. But the other question, or the other thing, well, maybe not question, is I too am very interested in moving towards solutions. And of course, what we could do is we could integrate these equations and get the same sort of solution that Dirac gets, and we'll get a Zitterbewegung. We know how to do that. But I think there are more interesting kinds of solutions that we should be going for, which is swapping what you're doing in the complex exponential way using I in the exponent for things that are really representing that are represented by quaternion-like entries. I think we should really, as a group, start writing down these solutions, just a few of us, and start thrashing out where the problems with these things lie. Because I think we have different views of where those. You're coming up with different kinds of sets of thinking on this as a mathematician. Peter's huge experience in this as well, with looking at the quaternions, is coming from a wealth of experience at playing with these things. I'm looking at it from yet another perspective as a solid state physicist and high energy physicist. So, but I think we should try and really push for solutions of these new kinds of equations that we're putting together, and start writing down those solutions. I think again,
certainly
would be great to do that. So we'll set something up to do that if people are interested, and of course everybody else is welcome. Anybody who wants will publicize these things are happening. If anybody else wants to sit in on such discussions, why don't we have a session which is kind of like an open session where we're trying to do that kind of thing and trying to go for solutions in public, and people can chip in if they want to.
But I have a feeling that we will end up with the same solutions, just formulated in another manner.
I think certainly that's true to a certain extent, Joachim. We're not going to find anything other than spherical harmonics and Bessel functions if we look at if we look at cylinders or spheres or anything else. That part of the solution will be the same. But I think the part that will be different is in Peter's three-part nilpotent system, where you can put the exponent to one side, as it were, and look at the nilpotent part as being an operator part and a vector part, or a multi-vector part. Is separate, but really there's a three-way connection. These things are each one stitched onto each of the other three by the fact that you need to end up with a zero here. And in fact, it's not just a zero that you've also got the one. You've got them both at once. And Lou's talking about that too. He's talking about putting that into his algebra as things that, 1 times 1 equals 1, circle next to circle is circle. But he's also got circle within circle, this different kind of connection, which goes to nothing at all, which of course is totally physically not allowed, Lou. Sorry, that's a no-no. Energy just vanishing, no, it has to go to something else physically. But I think what you should be putting in there.
Yeah, it was just the initial geometry that disappeared. We did. Well, I wasn't talking about the radiation.
Material.
John, stop there. You know, in an experiment, if you can't observe anything, it doesn't exist to the observer. Like if you have two electrons going into the superconducting condensate, you can't see them anymore.
No, they're not electrons anymore, Joachim.
No, so you don't see them anymore. You don't see anything happening in the superconductor. You just see them when you break a pair from the superconductor.
That's right.
But it still exists in the condensate.
No,
they are removing particles there, and you just can't see them.
No, they really don't exist as individual electrons in the condensate. What's happening in the condensate is you have a new particle. Okay, people tend to call it a Cooper pair, but I think it's a much deeper thing than that. I'd call it a dielectron, where you've got a spin-coupled pair, and that's how people are thinking about them. But this thing is no longer an electron. It's no more an electron than
it is a pair exchange of two electrons, or they are exchanged all the time. But at any time there are two.
It's a boson. It's a quasi-particle. It's a
and it carries energy. It takes energy.
Oh, yeah. Certainly carries energy. That's right. And
so it does exist.
Yeah, but I'm not saying Cooper, what we call a Cooper pair, doesn't exist. What I'm saying is once you drop into the superconducting stage, the individual electrons no longer exist as individual electrons. They now become dielectrons.
But that's the observer. We are the ones that can see electrons only.
Well, yeah, but to see an electron, you've exactly got to break it if it's a Cooper pair. So you can still imagine the electron must still be there, and you know if you warm it up, the electrons are all going to pop back out into existence. They haven't gone away, but they've become something else. You're dealing with a different quantum mechanical entity. You've got in a standard formulation of superconductivity, you've got a sort of quantum mechanics of a quantum mechanics. You've got a nested quantum mechanics. You've got the quantum mechanics of the Cooper pairing, and then you've got the quantum mechanics of the superconductor. So, but that's actually a little bit too simple, probably, eventually, to describe properly what's happening.
But I get the feeling that his operators can be used to describe what you when things enters and leave our observation space.
Well, that's right, and I'm thinking about these distinctions. What I put in place of the star is I put an exponential, a complex exponential that averages out over a period or over a number of periods to exactly nothing, equal plus, equal minus, with phases between them. So I'd say that when you put a circle within a circle physically, we're talking about something which looks like a wave function, a complex exponential physically. Would you? And I think in a previous talk, Lou was also saying, look, we've got something here which is the 1 to -1, which is really can also be seen as being a complex exponential, can be seen as something which is, and then properly one's going into a gauge theoretic approach of these things. And this is the gauge particle, it's e to the I theta, where theta is unobservable. So e to the I kx minus omega t, or k dot r minus omega t, is an unobservable. It's something that you don't know in a specific wave function. You might know relative phases, but not absolute phases. So that whole thing is an action, sort of ETs and KXs. These are all what Lou was calling omega here. They're the phase of that wave function. So would you be prepared to do that, Lou, to think about that circle within a circle as really just being something like a gauge function, like an e to the I theta function?
Yes, certainly. Certainly, it's worth thinking about. Another thing is getting back to the square root of -1.
Yeah.
There are two geometric points of view about the square root of -1, and maybe we compartmentalize them a little too much. One is that in the plane, it's a 90-degree rotation.
Yeah.
But in space for belt trick, it's a 180-degree rotation.
Exactly.
Right?
That's right.
So you turn turn the belt by 180 degrees, and then if you turn it twice, you get 360 degrees. You turn it 4 times, you get the 720 degrees, and that's the one that goes away. All right? Yeah. So you have this order 4 operator, which is a 180-degree rotation in space. And in any direction of space. It works in any direction of space. So it's right there. It's right there. It's just as close to you as the one that you've learned in the plane. Oh, my Sorry, my computer decided to go to sleep. Just a second.
Oh, sorry, but also in terms of the inversion, if you're looking at the general inversion of these algebras, you're also looking at something which is coming back to nothing at all after D4 or D2 after 4 operations. And if you're looking at Garnett's system, you're also looking at something that's coming back to the starting point in around a light speed box of order 4 colors. 4, 4, 4, 4, all the way down the line. The same thing. This is the structure of space-time in terms of what does space-time do for us? Well, it imposes that order 4 onto you for the belt trick and for the ultimate inverses and for the Dirac and for the Feynman chessboard as well. Of course, the kind of walk that you get down the Feynman chessboard. Isn't it beautiful?
Yeah, now there's another 4 in relation to the belt trick, because if you take a rectangle and you look at its symmetries, then that's Klein 4 group. And
Absolutely.
if you add signs to it, you get the quaternions.
Yes.
And adding signs to it is the same as adding a belt to it in a certain sense. You just keep track of where the belt got turned by putting signs on the card, if you like. And those are and that corresponds to the 4x4 matrices that represent the quaternions, if you like.
But isn't it?
So all of these things are fitting together. Most of these interpretations, except for the one of the commuting square root of -1, are fitting into non-commutative contexts like quaternions. The complex numbers are sort of peculiarly isolated in being commutative and and giving you trouble if you try to go to non-commutative algebras in the way that you've been using the complex numbers. I find that a little mysterious. There's this whole wonderful developed theory of functions of a complex variable, but the functions of a quaternionic variable are very hard.
Yes, that's right. I think just something from scratch. Oh, Garnett, sorry. Yes, please.
Could I just make a quick point that the Clifford algebra, when you sort of look at it and where it, if you think of taking, for example, think of the Pauli matrices, which are historically been used by physicists, and they've in a sense been constructed with a purpose. Think of sigma x and sigma z. They both have real eigenvalues, and when you multiply the two, you get another real matrix, which is skew symmetric and has eigenvalues that are plus and minus I. And because physicists want to use the Pauli matrices as vectors, they go, okay, well, when we multiply sigma x and sigma z, multiply that by I, and then all 3 Pauli matrices square to 1.
Right.
And so you can use them very nicely.
If you introduce that commuting square root of -1.
Yes. And so it's a lovely cheat that allows physicists to use the Pauli matrices really as quaternions and locating points in space. But if you stick to the original algebra and say, okay, let's just introduce these guys one at a time. Let's introduce sigma x, which is a switch. Sigma z is also a switch. Both of them are classical. You can throw them into classical statistical mechanics and use them for counting. Well, the thing is, when you throw both of them in, it brings in the product of the two, and it gives you something that's period 4, i.e. the matrix version of the square root of -1, which is not the square root of -1. It's actually got plus and minus I as eigenvalues, and it brings you directly to the Clifford algebra. And so
that's right.
And I think what you're finding when you look at how the Dirac equation works, you use the quaternions, the Pauli algebra, to locate points in space, but you use the sigma x times sigma z to have the switch. The switch is the thing that involves the time. And so when you try and step back from that, when you say, okay, I'm not going to keep track of special relativity at the same time, and so I'm going to throw away the Clifford algebra, or let is essentially the switch, which is this square root of -1, which we throw in and use complex numbers. It's not powerful enough by itself to give you both relativity and quantum mechanics, but it is powerful enough when you combine it with just the identity matrix. It's enough to give you non-relativistic quantum mechanics. So it's I think what you're seeing with the Majorana idea is that there are these two things. There's the Pauli matrices, which you can use in one way, and you step back from the Pauli matrices to get the Dirac algebra by saying, okay, forget trying to normalize the product of the two so that it's period 2, in which case you get the period 4, which is exactly what you need for in a sense, the clock that gives you space-time as opposed to space-time. So, well, sorry.
It's worth thinking about that. Yeah.
What is space-time?
Oh, space-time.
If we take the square root of -1 as the matrix, -1, 0 on the anti-diagonal, and then you just take it take it all by itself, which is what you do when you make it into complex numbers, into something that commutes with everybody else, then you have fixed the fact that it's you've ignored the fact that it's the product of the two Pauli matrices. You've ignored the fact that it is the epsilon times the eta in my terminology. You've ignored it. It's no longer a product, and it's no longer sitting in a non-commutative framework. It just is what it is. So it's a natural enough move, but it's a symbolic move. And I think it's a dangerous move. Yeah.
I think it's dangerous because you see, you can make the mathematics simpler like this and make it more general. But what you're losing, or what you're potentially losing, if you're sitting in CL13, for example, if you're sitting in the relativistic algebra, you can use the complex numbers to make everything squared to +1, if you like, or -1, or 2, 2, whatever you want, by putting them judiciously in different places, because you've got that extra degree of freedom. So what you're doing is you're giving your brain a chance to think things that are maybe not happening at all in nature, because you're going non-relativistic. And I think it was de Broglie who first pointed out that although the Dirac equation was a beautiful relativistic equation, the solutions that people were coming up with, post-Dirac, not Dirac himself, were themselves non-relativistic, because you're referring them to a specific frame where you have a kx minus omega t. So I think you might have just short-circuited your brain by putting the complex numbers in here if you're not very careful how you use them. I think that's a real danger.
Well, I think everybody who learns quantum mechanics at the beginning feels like they short-circuited their brain with this funny equation that involves the square root of -1.
Yeah.
So if you could start quantum mechanics itself without the square root of -1 in that funny jumped into position way, you might feel better about it.
But
you want me to do it for you?
So I think Peter would say, or we can ask him, he's here, that you shouldn't start quantum mechanics with the Schrodinger equation. You should start it with the Dirac equation.
If we want to get where we want to go to, we should start from here. Right?
So absolutely start with the Dirac equation, but I want to start Clifford algebra with Clifford's interpretation of it.
Mm-hmm.
Basically, Clifford's interpretation is to have an infinite series of commutative quaternion systems, some of which are incomplete. And an incomplete one becomes what we call complex numbers. So you have complete ones and incomplete ones. And the way I see
you're going to rationalize this commuting thing by saying, well, that's just a little incomplete one, which is 100%. Skittering around and talking to the others.
And if I look at it in this way, I say things that have got complete quaternions or no quaternions at all are conserved quantities. And things that have got incomplete ones, like space and time, are non-conserved quantities. Because space builds in an incomplete quaternion as well as a complete quaternion into its structure. And time is just an incomplete quaternion. And those are the varying non-conserved quantities. And I think they're looking around for completion, really. I think that's what they're really doing.
You can complete them off. You can complete them. If I'm understanding what you're saying, this is something that I've been chatting to John about, talking about the pairings. Space and time isn't a correct. My words are going to get mixed up here. You can pair those off, but with different things in order to make complete sets that work.
Yeah, you compare them off differently. You compare each parameter off with each other. But I'm saying that space and time both incorporate an incomplete quaternion set.
Yeah.
And they're the ones that are not fixed. They're the ones that are variable quantities. And the other quantities, the non-variable ones, are complete quaternions.
Wow, what an interesting discussion, gentlemen. We could probably go on all night, couldn't we? Or day, or morning, or whatever you are at the moment. But this is a to be continued, very much so. But let's think about this one and gather a group and invite people in and sort of not have a talk, but a sort of multiple dimensional thing like we're doing at the moment on this very topic. Think further. Innes is also going to give as a talk at some stage on the work that he's been doing on some of these different pairings and different setup. Well, I shouldn't say pairings. I should say Klein foregroup, shouldn't I? Really, Innes. So in terms of these things, very beautiful they are too. So I don't know when we're going to schedule that, and we might need to, heaven forbid, to go to 3 talks a week. Oh my, oh dearie me. That's good. Anyway, any more questions though? Anything else come up with other people? Yep.
You started to mention about I have another name or model or view of the Cooper pair. You call it, what did you call it?
A dielectron.
So can you talk about that?
Yes. Oh, you want me to give a talk on it? Yes, I can. Yes, later. Okay.
Oh, that'd be great.
A medium length one, yes.
Could you start from fermions and go to Cooper pair?
Yes, I can start with fermions. I can go to fermions from bosons in 2 different directions. So we could call the talk fermions from bosons and bosons from fermions, if you like.
Yeah, the duality about electrons and bosons.
How to make fermions from bosons and how to make bosons from fermions.
And maybe you can think about this talk when you do that and relate to it.
I think we're all developing each other's ideas here, and slowly lots of things are dawning. I'm learning a lot from you guys, I have to say. So,
creation and annihilation operators, for example, you can just have one slide of it.
I want to talk about boring stuff like that.
Shit.
There are thick textbooks about creation and annihilation operators, and a lot of nonsense too. Listen to what people.
Commuting and anti-commuting words. The observation is in the fermion word, and you need to have anti-commuting things then.
Yeah, but that's not the whole story. The whole story is, of course, always at a deeper level, or there are always levels within levels of these things. But yeah, I can give a talk on that at some stage down the line. I'd be delighted to.
There's a mathematical comment I wanted to make about the structure of what happened at the end of my talk. So if you look at it again, you might look at this. When we wrote down the Dirac equation, then just as you would find in Peter or in a book on the Dirac, using the Dirac equation, the algebra got jumped up when we went to 3 dimensions instead of 1 dimension of space. And and all you had to do in the original Dirac equation was jump up the algebra in the XYZ, and you didn't have to that extra mirrored algebra didn't have to do anything funny with regard to the other one. So it's sort of factored into 2 pieces: the outer one and the inner one for the momentum. And that got mixed up in the Majorana equation. The operators and their mirror versions of the operators got mixed up across the momentum parts, so that you couldn't just factor them out and see algebra times algebra. And there didn't seem to be any, and there doesn't seem to be any way to solve the problem of writing it purely real without having it mixed up.
I think
so. This speaks back to the question, well, what does it mean to write it entirely real? what does it mean to get rid of the square roots of -1?
Mm-hmm.
In a technical way, it's asking that question again.
I think what it's doing is it's restricting the allowed solutions eventually. What it's doing is it's an extra condition, and I think that what this leads to are things that are essentially chiral. And so if one's going to the real representation, this is a chiral representation as well. And the chirality of some of the base elements under products are different for different elements if one doesn't introduce the square root of -1, which one can use to fix the problem. But I don't think it's a problem, because I think one has to be very careful. One can introduce something which works in one area and then look at that area. But the algebra one, if one's looking for an algebra which does all of the things one needs to, and you're quite right, it's a big problem going to purely real Dirac algebra for some of the things one would like to have in the algebra, and the algebra gets quite hairy when you start trying to take bits out, like the kind of products you'd like to have. But the question is are you fooling yourself when you do that? You're making it easier to calculate things, but the question is, can you describe those things without having that degree of freedom to describe the kind of solutions you want? Or do those solutions, for example, in the neutrino equation, where you have a right-handed right-handed neutrino and left-handed antineutrino, but not the equivalent ones? For example, there are places where nature is handed. The man in the mirror is non-physical. If you see him acting, a person coming towards you acting like the man in the mirror, run very fast, because we're probably talking about something which is going to explode when it hits you. Chirality is in nature at the level of everything, from particles themselves up to life as well. DNA is handed, right? So yeah, I think it's not necessarily, although I can see that it's a mathematical problem, it's not necessarily a physical problem to not use the square root of -1. But this is something we need to get into the actual crux of the matter, where it breaks down. Say that one cannot do this because this doesn't work, and then see if those solutions are exactly ones that you don't see that mirror image in nature. Or so that's a very interesting set of problems, because the mathematics, the real mathematics, is not very well behaved. so it does make life difficult in some way. But it's an interesting kind of difficulty. At least I find it interesting. So I think that's something we need to look at and see whether or not we can make it work in terms of proper solutions. Okay.
Yeah. Thank you.
Right. Thanks very much, Lou. I guess, John, I guess that's a good stopping point then.
Oof. Well, thank you very much, everybody. That was a lovely, brilliant talk again, Lou. Thank you very much for the talk. You're only halfway through the talk, unfortunately. You didn't realize that, didn't you?
Well, the other half isn't done yet.
We'll schedule in for 3.5 months' time, the Christmas lecture.
Okay, fine. Christmas. Ah,
well, okay, maybe not that far away. Yeah, okay, good. Yes, well, that's, yeah, to be continued next year. Perhaps the conference when we actually manage to hold it. Okay, right, gentlemen. Well, a pleasure to see you all. There'll be another couple of talks coming up next week. So, one of them is already scheduled. Garnet is going to be talking, I think, on Sunday next. If you still like to go for that slot, Garnet, then
lost it.
Sure.
Are you still happy about that one, Garnet? We couldn't hear you just now.
Yeah, sure. That will work well.
Well, I'll be circulating something as usual on Thursday for Garnet's talk. So let's draw this one to a close, everybody. Good night, good morning, good afternoon, sleep well, take care of yourselves, and talk to you all later. Bye for now.